When you deploy a standard conversational model to run an autonomous agent loop, it usually breaks. After 10 or 15 steps of navigating file structures, writing code, and calling tools, the system loses its threat. Ant Group's Inclusion AI released the Ring 2.61T architecture to address the specific point of failure. It is a 1 trillion parameter mixture of experts model released under an open MIT license. While many models prioritize conversational fluidity, this architecture functions as a continuous execution engine, prioritizing the persistence of multi-step tasks. The model uses a new architecture and a specialized training pipeline to solve the decay and performance that typically occurs over long horizons. Creating reliable autonomous systems is no longer a matter of finding the right prompt, it is a raw architectural requirement. To see how well that architecture holds up, we look at PinchBench, an evaluation that tests a model's ability to complete actual workflows across multiple steps. Here, Ring 2.61T scored an 87.60. This chart shows the official PinchBench results. Ring 2.61T on the left outperforms both GPT 5.4 and Gemini 3.1 Pro. This scoring gap means the model is better at inspecting code, running tests, and revising work without losing its objective. Notice the labels at the bottom. Ring achieved the score operating in its standard high setting, beating the top-tier maximum effort modes of its competitors. These figures come directly from Inclusion AI. The open-source community is still waiting for neutral third-party indexes to verify the exact numbers. The mechanics driving these claims are documented. They rely on two specific engineering breakthroughs: a parameterizable reasoning budget and an asynchronous approach to reinforcement learning. The open weights landscape is moving past models that can pass static academic exams. They are now actively competing on operational execution. To process complex loops without massive latency, Ring 2.61T relies on a highly sparse mixture of experts architecture. Instead of forcing every piece of data through the entire neural network, a mixture of expert system evaluates an incoming token and routes it only to specialized subnetworks. While the model stores 1 trillion total parameters, it activates roughly 63 billion per token. This keeps the compute latency low and the API costs affordable, while retaining the vast knowledge base of a trillion parameter system. Processing tokens cheaply is only half the equation. An agent also needs to hold the entire history of its actions in memory, without the system crashing. Standard self-attention algorithms scale quadratically, meaning memory demands explode as the context grows. To fix this, the engineers implemented hybrid linear attention. This design structures the network into layer groups, blending highly efficient linear attention blocks with standard grouped query attention. It reduces the time to first token to a quarter of what traditional models require. The resulting system supports an active context window of 256,000 tokens. That gives the model enough room to ingest a 200-page API document and keep it perfectly referenced throughout its workflow. By pairing sparse activation with linear attention, the architecture physically supports the hardware demands of endless autonomous loops. Once the hardware capacity is secured, developers need a way to control how the model spends its compute. Ring 2.61T does this through an adjustable reasoning effort mechanism. It turns the model's internal chain of thought into a configurable parameter. You dictate exactly how much cognitive budget the model uses per task. The system defaults to high mode, calibrated for high-frequency operations like organizing files, scheduling tool calls, or breaking down a project plan. It bypasses deep thinking networks not needed for administrative execution, keeping token costs low enough to run agents continuously. When tasks demand intense logic, like parsing math theorems, the system switches to X-high mode, activating multi-path exploration and burning maximum compute to find the correct answer. It is strictly in this maximum effort mode that the model scored a 95.83 on the AIM-26 math benchmark. Decoupling the depth of reasoning from the standard text generation allows developers to afford continuous autonomous systems without draining their API budgets on unnecessary logic checks. Training a model of this size to think requires reinforcement learning, which introduces a primary training bottleneck. At a trillion parameter scale, the training engine and the inference engine frequently misalign. In traditional synchronous reinforcement learning, the system samples a policy, halts to calculate parameter updates, and forces massive GPU clusters to sit idle while the network synchronizes. To prevent this, Inclusion AI utilized asynchronous reinforcement learning, fully decoupling the sampling pipeline from the parameter updates. The sampling and updating run in parallel. This keeps the hardware continuously saturated with data, maximizing the throughput of the cluster. But as the training cycles extend and the reasoning chains grow longer, the model faces policy collapse, where the logic breaks down and diverges into noise. The engineering team built an algorithm called IcePop to counteract this degradation. IcePop acts as a token-level discrepancy masking system. It monitors the engine and actively suppresses extreme, noisy signals caused by mismatched reasoning paths. By cooling down these mathematical mismatches, the algorithm stops the training and inference engines from drifting apart over long horizons. With the drift stabilized, the model's complex reasoning capabilities can safely compound over weeks of extended reinforcement learning. The combination of asynchronous RL and IcePop provides the framework needed to keep massive neural networks from forgetting how to think during the training process. There is a misconception that because Ring 2.61T is open weights, you can easily pull it down and run it locally. Natively hosting a trillion parameter model in FP8 requires cluster-level infrastructure. You need multi-node pipeline and tensor parallelism. Practically, that means spinning up roughly 32 high-end data center GPUs across multiple physical servers. For engineers who need to self-host, Inclusion AI provides two smaller variants trained on the identical reasoning lineage, Ring Flash and Ring Mini. The 100 billion parameter Ring Flash activates just 6.1 billion parameters per token, allowing it to run efficiently on a single high-end workstation. Regardless of which size you deploy, the most valuable asset here is the legal framework. The entire Ring family is released under a clean MIT license. Competing models often ship with bespoke licenses that restrict commercial use or limit derivative works. The MIT license removes those caveats entirely, giving enterprise teams full control over fine-tuning and deployment. By combining an unencumbered license with a sparse, stable architecture, Ant Group has delivered an infrastructure-grade execution engine. It establishes a clear, practical standard for what open-weight systems can autonomously accomplish.